Thanks for that, Liam. You've noticed that there is no title on this. I've just called it PFAS. Reason for that is, where do we start? Honestly, I just had no idea what to call it. So, and because things are changing so quickly, I thought we'll just call it PFAS to start with, but I have just put what you do need to know about it. And I really decided on this title after the Four Corners program on Monday night. That was actually not too bad. I thought it was going to be a bit more biased than what it was, but I was actually quite pleased with the way they actually presented the scientific side of PFAS. So there is increasing concern worldwide about the environmental and human health impacts from the use of PFAS. This is a quote from the heads of EPAs around Australia that have formed a group and have just released a draft document that's not sure if it's still open for comment, but it was a short while ago. So there is concern. Is that concern valid or not? We'll wait and see. So PFAS refers to a large group of chemicals, and at the moment there's at least 28 of them that we currently monitor routinely for, and those species of PFAS are growing. Most of the research that's been done has been on PFOS and PFOA. Very little research has been done on the precursor or breakdown chemicals resulting from that. They comprise of an 8-carbon chain with a hydrophilic head and a hydrophobic tail. So they're so different from the chemicals that we normally work with. We work with toxic metals, toxic organics, and now we've got these PFAS chemicals. They behave completely differently from what we've seen in the past. So is actually using our models for developing guidelines in particular that we've used for organics and metals, are they appropriate for using with these chemicals? We've had discussions with regulators and still haven't resolved it. But at the moment, we're working with what we've got, put it that way. These organisms, keep calling them organisms, these chemicals partition between water and sediments and soils in different ways. So PFOS has been used in a wide range of industrial uses, and you will find it in the dust in your homes. It is in carpets, it's in scotch-guarded furniture, Gore-Tex clothing, anything that's water repellent or stain repellent would have had some sort of PFOS or PFAS chemical in it. So you are exposed to it constantly. And PFOA is in Teflon. Hands up who uses Teflon cookware. I know I do. So you're ingesting these chemicals on a constant basis. However, it's not being made now, so the amount of PFOS and PFOA entering the environment has decreased a huge amount, and we're actually seeing that in the concentration, in the blood level concentrations in Australian populations. So we know that it is decreasing in the environment. Oh, actually, I'll just go back and explain the actual tail, which is those carbon-fluorine bonds, are hydrophobic, and then we've got our hydrophilic head. So the thing about these chemicals, they're really, really stable. They don't break down in the environment. There's no photolysis, there's no biodegradation. Only high temperatures will actually break those bonds. And the thing is, it makes it really stable. And the most important thing from our perspective as humans is we have no detoxification enzymes to break these chemicals down. So they are stable in our body. Now, I think it's really important to note that a lot of the cancers that are caused in humans from chemicals are a result of overactivation of detoxification enzymes and the resulting breakdown products. So this chemical, yes, it's sitting in our body, it's binding onto proteins, but it's not getting that reaction that we would normally see with something like a dioxin that we know causes cancer. So we're not seeing that with this chemical. It's very stable in the environment, it's very, very stable in our bodies. And I think that's something that I don't know if people don't know, but it's not something that a lot of people are aware of. The problem with it being so stable, it does get transported throughout the world. We've found PFOS in particular in penguins in the Antarctic. We've found it in dolphins and whales in the Arctic. We know that it's very widespread throughout the world, and the fact that it has been used in firefighting, so it's actually going up into the atmosphere, very volatile, well, it's not volatile, sorry, but it does go into the atmosphere where it can get very widespread. So that's one of the big issues that we do have with these chemicals, is that you find them everywhere. And when we move the focus down to, say, firefighting, fire training areas, that we do see the PFOS and PFOA moving through the contaminated soil into the groundwater and then into the surrounding surface waters as well. So we are seeing that. So they do partition between the water and soil. So normally what we see is the PFAS moving through the system a lot faster. If you saw the hydrophilic head, it is a bit bigger in the PFOA, so that's actually going to move through the water phase a lot faster. The PFOS is more associated with your soils and sediments, so that will move through your system slower, which is why I think we're seeing down at Catherine, it's not so much PFOA in the system, that's already moved through, but the PFOS is now moving behind it at a slower rate. I think, well, I won't. So what we're seeing is there is that amount of organic matter in the soils and sediments that will preferentially bind the PFOS. So I've just got a quick diagram of the water phase up the top. So the PFOA usually ends up in the water and the PFOS will end up in the sediments. So the eventual fate, and this is what we're seeing in countries like China where they do have very high concentrations, what we'll find is the marine sediments will be the ultimate sink for PFOS. So human health, I will say now, is not my area, but I thought because everybody's really interested, I will just put some results of some recent research up and tell you how the water quality, the drinking water quality guidelines have been derived. So consumption of food, particularly fish, we know that fish do bioaccumulate PFOS very readily, not so much PFOA. It is detected in human blood, tissues and breast milk in particular, so that's another pathway for babies to increase their PFOS uptake. What's really interesting is it does have a half-life of 4 years, approximately 4 years in humans, and already since we've been monitoring human blood serum levels in Australia, we're actually seeing a decrease over the past 12 years, and it is a linear decrease that matches up to that 4-year half-life. So we know that we're not being exposed to more PFOS, so that's being limited, and we are actually reducing the concentrations in humans in Australia. So when it leaves the body, guess where it ends up? Sewage, probably in the biosolids, so quite high levels in biosolids. And that's got implications for using biosolids in agriculture as well. I've done a lot of research in the US in that particular area. So the thing is, it does bind onto proteins. So different from our organic chemicals that bind to your liver, to fatty tissues, these bind to proteins. So anything that's got to do with blood or high protein, you are going to see more PFOS. And I think it's important to note that no epidemiological studies to date have confidently or statistically implicated PFOS in any adverse impacts on humans. And what's really important, I think, more so for us being Australians, is the concentrations that we see in the Australian blood serums are not related to any toxic effects whatsoever. So we're not seeing them, even in firefighters, we're not seeing any adverse harm related back to PFOS. I will qualify that. So the mode of toxic action is actually derived from animal studies where they're using very high concentrations in laboratory studies. So hepatocarcinogenicity in rats, so if you look at rats down the bottom there, we're going up to 78 milligrams per litre. So it's pretty high in a very small organism. So the results down the bottom, the monkeys, slight reversible changes in ALAT, so that's liver enzymes, blood serum, 35. Rats, increased liver weight and liver enzymes detected, and benign changes that we're seeing. So these numbers are actually the numbers that have been used in deriving the Human Health Drinking Water Guidelines. What we do is put a application factor on, and in the case of Australia for PFOS and PFOA, they've actually used an application factor of 30. So normally we would use an application factor of about 10, is that correct? But in this case, because we don't know the long-term effects, they've used an application of 30 because we follow the precautionary principle. So the drinking water levels are probably a little bit lower compared to a lot of other chemicals that we're used to. So that precautionary principle is based on insufficient human information. A lot of the other chemicals, we've got lead, mercury, we know those human effects, but with these chemicals we don't know the long-term human effects, which is why we're making that application factor a lot higher. So the Australian Government Department of Health again agrees that we haven't actually found any significant adverse effects with humans with these chemicals. So what I've done, I've just put the TDI, the tolerable daily intake, and the drinking water guidelines, just to put it into perspective. So by looking at these numbers, dieldrin that we know is a carcinogenic chemical. Drinking water guidelines for PFOS are an order of magnitude lower. So that would make you think, oh my goodness, PFOS is an order of magnitude more toxic. Well, we don't know. Well, it's not, because we've seen it from the toxicity results, but we don't know the long-term effects. So that's really all I wanted to show on that one, but it's just that precautionary principle makes these numbers artificially low. Ecological effects, which is a bit more my area, we are seeing impacts again in laboratory testing. So we're using high concentrations to actually get some adverse impacts happening to these organisms. There is potential for chronic impacts. We've actually seen that in multi-generational studies in fish, where we do see a reduction in fish offspring numbers in the second generation of exposure. So we have been seeing that in fish. And what probably is the most worrying thing is that it does bioaccumulate through the food chain. And as I said before, the small fish have quite high body burdens, quite high concentrations. So it's those bird-eating fish, other way around. The birds that eat fish are the ones that are actually, you'll probably end up seeing the highest concentrations from that biomagnification up through the food chain. However, one thing with these organisms, we do actually see rapid depuration with them, and I've got a couple of slides on that from new research. So again, it's still binding onto the blood proteins, and it can affect intercellular communication, which can impact on the immune system. And if you saw on Monday night on Four Corners, there was an American doctor that was saying that PFOS has been implicated in immune dysfunction in children. So, you know, this PFOS in combination with something else may have that result. So it's not out of the question that something like that might happen. So in environmental studies, we're finding that the concentrations in the environment are not toxic to the exposed organisms. However, it's that bioaccumulation and biomagnification effect that will be driving how we manage PFOS and PFOA in the environment. So these are the guidelines for freshwater. So New South Wales, EPA and OEH are actually promoting the use of the freshwater guidelines at 99% species protection, which is below detection levels. So what that means is if you do not detect PFOS in your sample, you are above guidelines. So how do we manage that? That's a real issue that we're having as environmental scientists in Australia. So what it's saying is everything that we sample is above guidelines, and we do have to do further investigation. And I just put this up to compare. So as I said, dioxin's our number one cancer causing chemical. That's given a 1. Everything else is related back to dioxin. So again, PFOS is 3 times lower than dioxin for a guideline value. So how do we apply these guidelines? So what we've been doing is ecological risk assessments, which is the way the new ANZECC guidelines are going. They actually want to get away from using guidelines and go down the risk assessment approach. So that's what we're doing at the moment. So the NEPM and ANZECC do have that risk set up, and we are using that. So risk equals exposure and the toxicity threshold. And this is just a quick overview of what a risk assessment looks like. Work out what's going on site, delineate it, manage it, and remediate if necessary. So recent gains in knowledge, really interesting work that's been published by New South Wales Fishery around Williamtown, that they've been monitoring fish and crustaceans in that area, that what they're finding is there's no relationships between trophic levels in fish. It's got more to do with the habitat and diet. And there doesn't seem to be very much relationship between distance from source either. Because what we're finding is the source is mainly in freshwater, and as we're moving out to marine systems, it behaves differently. So we're getting different uptakes through the fish. So it's quite a complicated process between that marine and freshwater system. Variable in marine crustaceans, but what was really interesting in some work that I did was in the freshwater yabbies that burrow down into the sediment. So I've said that sediments are a sink for PFOS. So expecting something that lives in the sediment to have really high concentrations, didn't. So something's going on there, so we need to know what's happening with those yabbies and why their concentrations are so low. And this is what I think is really interesting, is the rapidity, is that a word, of the depuration, of actually removing this chemical from the system. That it's within hours, that the half-life of the chemical within the system, once it's removed from source. And if you can imagine a larger fish that's swimming in and out, swims in, has a feed, takes some up through the water, goes off, gets depurated within a matter of hours. And in New South Wales, where this work was done, oysters in particular, because they shut down the oyster farming at Williamtown, but oysters in New South Wales need to go through a 5-day depuration. So from the research that fisheries have done, they've shown that within that 5 days, PFOS and PFOA are out of the system and the oysters are safe to eat. So, yeah, as I said, Australia's stopped using it. Most of the high concentrations are around those firefighting training areas, and that's what we're focusing on with our research at the moment, research for our clients at the moment. But I just wanted to really talk about the Port River dolphin study. The dolphins in the Port River, one of the most contaminated rivers in the world that's actually undergone a clean-up over the last 10 years. The dolphins in the river, and the Swan River as well actually, have the highest concentrations of PFAS anywhere in the world, and they're a factor of 10 to 20 times higher than any other organism in the world. However, at the same time we're measuring those, we're finding that the number of dolphins in the area and the number of babies they're having is increasing. The population of the dolphins in the Port River are the healthiest it's ever been. So we need to take that into account as well when we're just looking at these long-term effects. How does this relate back to humans? Can we do that? I don't know. Probably maybe better than rats. I don't know. But it's something to take into account. So this is a study that we need to keep following to see what's going on. So we're up to an F2 generation with these dolphins. So we need to see what happens with the next generation. So I'd really just like to leave you with this take-home message is our Australian way of doing things, the degree of uncertainty with this chemical and the precautionary principle that we apply here will result in an overestimation of perceived effects and overly conservative guideline values. And I think I'll just leave it there. Thank you.
Okay, we're out of time, and I feel if I open up a PFAS conversation, it'll take the whole day. But has anybody got one quick, really burning question? Yeah, Jennifer.
Yeah, just a question about the plant uptake. You referred to the biosolids or through water. What's the mechanism? Or what's the evidence there?
So what we're finding, the PFOA is in the roots, and the PFOS doesn't really get taken up. So, and it doesn't, neither PFOS or PFOA will actually get into the fruit.
So they could actually lead to mango at the end.
Yes, I think they're doing some testing at the moment, and I think they'll find that the tests come out okay.
Okay.
Thank you.
Thank you.